guys! Today we're starting chapter 5. We're going to start today with drawing Lewis structures. Remember, we started drawing them for elements, and now we're going to draw them for compounds. Mostly we draw them for covalent or molecular shapes. Occasionally we'll do those ionic ones, which you saw in chapter 4. So there are different bonding theories, and these show us the different ways they interact, the molecules do. But the main one we're going to focus on is Lewis theory, which we already talked about. Remember, it's going to focus on those valence electrons. Okay, it's also going to help us predict properties of molecules like stability, shape, size, even polarity we'll get to. So, why do atoms bond? It has to do with them wanting to be in a more stable configuration, but we do have to keep in mind those nucleus-nucleus repulsions, the electron-electron repulsions, and then those nucleus-to-electron attractions. So remember, we've got 3 types of bonds, an ionic, a covalent, and a metallic. Remember, for ionic, we're looking at metal and nonmetal, and they're transferred. The electrons are transferred. For covalent, they're nonmetals only. Those electrons are shared. Metallic, this one's a new one. We did mention it before, but we didn't talk about the electrons. So metallics are going to be only metals bonding. But here electrons are pooled. And it says down here there's a communal sharing. We like to say these are delocalized electrons. So basically what they can do, they're not attached to their specific atom anymore or element. They just get to move around freely in the metallic bonds. So this is why metals are such great conductors and why they're able to be shaped easily, because the electrons are just moving around. So for bond polarity, which is the first thing we're going to talk about with the bonds, this is unequal sharing. Then it's polar. So unequal sharing is going to be classified as a polar bond. Okay. Polar covalent bond, normally we just say polar bond, but again, it's that unequal sharing. So really, it's that one atom is pulling the electrons towards itself more than a different atom in the bond. So electronegativity is our last and final trend. Remember, we talked about trends in chapter 3. So electronegativity looks just like ionization energy, but these do not include noble gases. Okay, and that's because the definition of electronegativity is that it wants to pull an electron towards itself, and noble gases don't want to pull any extra electrons because they're already full. Okay, so we ignore the noble gases, which means fluorine is the most electronegative element, and francium would be the least. And the ability to attract those electrons to itself, that's electronegativity, and it's within a specific bond. So it's from one atom to another one. So here we see hydrogen is not super electronegative, and you can see here, this is a very small region in comparison to this larger region where it's electron dense. So in this situation, fluorine is the much more electronegative element, even if you don't have the numbers. So pure covalent is a nonpolar bond. So I would normally call this nonpolar or pure covalent. That's equal sharing. For you to determine this, they need to be the same element. And I'll talk about that in a minute. Because see, they have these numbers attached to them, but you're not going to have a chart. So you just need to go based on the arrows, these arrows. Which one's more electronegative? Polar covalent is that unequal sharing. Okay, and don't forget ionic will be metal and nonmetal. Always. Or polyatomic, don't forget about the polyatomics. So here, this is what I'm talking about for pure covalent. This is how you know. So Cl, they are equal in electronegativity, so you know that they are nonpolar. HCl, though, those are different, and they're covalent, so they're polar. And then, again, when the electrons are so polar they've been transferred, they're ionic, metal and nonmetal. Okay, this goes through dipole moments. That's just that arrow that was pointed here. So on this one, it would be this direction. And that's how you would draw a dipole moment. It points towards the negative side. Also notice these little weird S's. Those are lowercase delta symbols, and they just means partial. So in this example, this is the chlorine and the hydrogen. The partial negative is going to be on the chlorine because it's more electronegative. Then the other one becomes partial positive, which is that hydrogen. Okay, there's also ionic character. We're not really going to go into that. Okay, but here we are going to do these practice problems. We're looking for ionic, polar, or let's call this nonpolar. Okay, so remember, if they're covalent, our choices are polar or nonpolar. If it's a metal and a nonmetal, it's ionic. So this first one is automatically ionic because strontium is a metal. These other two, they are different elements, so these are both polar. Now, I will tell you, this PowerPoint's going to tell you one of them is nonpolar, and that's because of their values. But again, you're not going to have values on test day, nor do I want you to use values. I only want you to tell me it's nonpolar if they're the same exact element, like this, I and I. That's the only time I want to see you tell me nonpolar for a bond. Okay, and remember that Lewis theory talks about the octet rule, and that it'll predict that atoms will be most stable when they have an octet of valence electrons, or 8 of them. So just make sure as we're going through this Lewis structure process and we start drawing them, most elements are going to want to have 8 dots, or valence electrons. Okay, and just remember that compounds that are of nonmetals are made of little individual molecule units, which we see a lot in particulate diagrams. There will be exceptions to the octet rule, which we will talk about, but for now, the biggest one you need to know is hydrogen. Hydrogen will only get 2 electrons at most. Really, it's what it always wants. And terminal means outside. So these are the steps to drawing a Lewis structure. Step 1, write the correct structure, where the least electronegative element goes in the center. Generally, it's the first element shown, or the one that just has 1 atom of that type. That's not always, but here's the deal. Hydrogen cannot go on the inside. It cannot. It has to be terminal, which is that outside atom, and it's because it only holds 2 electrons at most. Next thing, count total valence electrons. So they're going with the water example, so they're counting, well, they're not doing water anymore. So hydrogen has 1, there's 2 of them, oxygen has 6, so we've got 8 if we were doing water. Okay, we're going to distribute electrons among the atoms in the molecule giving octets. So it says outside first, then inside atoms. Duets in the case of hydrogen. Really, first it's going to be bond to center, and then it's outside, inside. You have to go in this order, otherwise they don't come out looking right. Okay? Please make sure you're paying attention to that. If something lacks an octet, that's when you double or triple bond. But that's only once you've run out of electrons. And remember these CNOPs? Those are the only elements that can double and triple bond. And remember, they're to one another. Okay, so first example, NH3. This is what a skeletal structure looks like. Hydrogen cannot go in the middle. Step 2, valence electrons. I've got 5 from nitrogen, 1 from hydrogen, but I have 3 hydrogen. So I have 8 valence electrons. That's step 2. Step 3 is to bond them with a single bond. Once you've done that, subtract electrons. So I've got 2 left because I use 2 per line. Okay, outside cannot get any in this situation, so then the extra 2 go on the inside. Then you go back and check, does everything that have 8, besides hydrogen, Yes, it does. Okay, let's do this one. H2CO. So remember, the rule is the least electronegative element goes in the center, except hydrogen. So the thing farthest from fluorine is carbon. But if you don't have to go with that process for carbon ones, because if carbon is present, it's going to be in the center, period. Okay, next step, count valence. I've got 2 hydrogens plus 4 from carbon plus 6 from oxygen, so I get 12. I have used 6 in my lines that I already drew. So then we distribute to the outside atom. It can hold 8. It already has 2, so all 6 can go on that one. So once you're out of electrons, it's great. And please, please, please don't put more on there than you have, because you can't create or destroy matter. Okay, so at this point, we check to make sure everything has 8. If you look, oxygen has 8, but carbon only has 6. This is the situation where we double bond. I've got no leftover electrons, and something else needs them. So what I do is I move the electrons to make a double bond. Okay, let's do another one. Carbon dioxide. Okay, skeletal structure. I've got 4 plus 2 times 6, so that's 16. Bond them. Minus 4. So I've got 12. Distribute to the outside. Each can get 6 dots on the outside because they only have a single bond. That means I use 12. Once we're out of electrons, remember to go back and count. Carbon only has 4. So I am going to move some from oxygen. Now carbon has 6. But notice this oxygen with the double bond now has 8. And then I'm going to move some from the other one. Okay, we do want them to be as symmetrical as possible, so if you have the option to pull from both sides, please do. Okay, this is going to be our last example like this. Carbon monoxide, I've got 4 plus 6 is 10. Minus 2 is 8. Okay, I don't care how you distribute these. I'm going to do it evenly. It doesn't matter. Neither will have 8. Okay, so I'm going to move a pair. Now carbon has 8, but oxygen only has 6. I'm going to move another pair. Okay, really this is how you would normally draw them. I don't care how it looks, as long as they're in pairs, the lone ones. Okay, also, I don't love you putting dots between them. I would really prefer lines. Also, why would you put dots when lines are so much faster to draw? Okay. Now let's talk about polyatomics. So just remember that polyatomics have that extra electron moved. So skeletal structure, 5 plus 4 times 1. And then this plus 1 means it lost 1. So I'm going to subtract. So I've got 5 plus 4 is 9 minus 1. So I've got 8. We bond them. Hey, by the way, that's 8. Nitrogen has 8. It's great. The only extra part for polyatomics is that they get brackets with a charge. Okay, one more, hypochlorite. So we've got Cl and O. I've got 7 plus 6 plus minus means add 1. So I've got 14 electrons. I'm going to bond them. 12. I'm going to put 6 dots on each to get 8. Okay, when I do that, everything has 8. There's a charge, bracket it in. And that is it for basic Lewis structures. We will do some more complicated Lewis structures on the next video. Y'all have a great day.